From today, I'm going to talk about a new topic about integration. So I just want to know, I want to check, is anyone who's doing the project 9 on the final presentation? Raise your hand if you're doing project 9 in the first project task in the final presentation. So not everyone is here, so I just want to check if I have to cover up to the project 9 or not, because we only have 3 weeks to cover, and we only have 3 weeks and we need to cover 3 chapters. So the first chapter on chapter 7 is basically the integration of single variable, but it also contains the multivariable. It's a multiple integration, but I think I can make into 3 weeks, but I'm not sure if I have time to cover entire project topics with the coding. So if I don't have time to cover the coding part, then I will record another separate video and upload it. So anyway, so let's start with the integration or integral. So this is, well, I would say the big second pillar of this calculus. Whenever you learn calculus, you learn about the differentiation and the integration. And again, to summarize what we learned in the previous time, in the differentiation part, the most important part is the chain rule. Okay, the chain rule derives the gradient, and gradient derives the gradient descent, and then so on, so optimization. And integration part is about geometry, actually. So integration is about geometry. So people think that integration is kind of an opposite of differentiation, but it's not at all. It's not about the differentiation. It's a completely different story, but they are connected. So I'm going to ask you this simple question. How do we compute the area of this how do you compute the area of this domain? So this domain is surrounded by 3 lines. One is the graph of y equals to x squared, and in between and x-axis, and in between 0 and 1. So basically there are 3 lines: x-axis, x equals to 1 vertical line, and the line of graph. How do we compute the graph? How do we compute the area? Yeah, you can do the integral. That's the point. Yeah. So the area, so if you think about the area, that's a very geometric object, right? Geometric concept. So how do you compute the area? There is only one type of region that you can compute the area. The area of a rectangle is the only thing you can compute the area intuitively. So if you have area, if you have a region, the rectangular region, then the area of that region is just height times width, right? So area of A times B times C times D is just B minus A times D minus C. And other than this principle, like area of a rectangle, you have no way of measuring area, right? What kind of area can you think of? Well, for example, a circle, maybe you can say, okay, well, you know what the area of a circle is. That's kind of cheating, because when you say the area of a circle is 2r squared, it says that pi something gives you the area. So there is an area. We know that there is an area, but we just defined pi so that it is used to call it as an area, right? It's not that pi exists first and the area is pi times r squared. We defined pi with accordance with the area concept. So where this area actually came from? It came from integral. So think about this area of this graph under the curve, y equals to x squared. So I think if you listen carefully to, I don't know whether the high school even teaches these days about this. So when you take these subdivisions of these areas or region into smaller pieces by subdividing the x-axis from 0 to 1, you have lots of the short intervals, right? And for each short interval, you're not going to compute the exact area under the curve. You're going to approximate the area under the curve by the area of a rectangle. So we know how to compute this area of a rectangle, right? So what is it? So suppose that we have subdivided our interval from 0 to 1 by x0 to, let's say this is x0, and this is, let's say, xn, okay? So which means that we have n subinterval total, and this start from xi minus 1 to xi. So if I make it bigger, so this is what it looked like for exaggeration. So this is xi minus 1, and this is xi. So this is i's interval from xi minus 1 to xi. And what is the height? So it now depends on height. The area depends on height. I know the width here. So height has to be something reflecting the actual area, right? But there's no height of the single height of this actual area. So we need to decide which height we take. We cannot take a height far away from the actual height, but we cannot make it too small, right? You have to choose somewhere in between the height of actual graph. So let's say I take a height, let's say to the right here. So this is the graph of actual curve of the actual graph. And let's say I take a height of value of function at the right end of my I subdivision. So then the area, this area of rectangle, is going to be xi minus 1 times fxi, right? And then this is going to be similar to area under the curve on this small interval, xi minus 1 to xi. So and then what do we do? So we have done this for small subinterval. We're gonna do it for every subinterval, and then add all the area of a rectangle, and then approximately say that this sum of the area of a rectangle is the area of the region under the curve. But it's just an approximation. So let's at least do that here. So if I take the sum of all the area, xi minus 1 times fxi, from first subinterval to the last subinterval, that is going to be similar to the total area from 0 to 1, right? But how do we get the exact area? What do we do? What should we do to get the exact area? Because this is there's an error. Here is an error. So this is the area what we want. We have an excess area here. So this is an error. We want to decrease the error. What's the only way we can decrease the error? How do we decrease this gap? If you use the height of the rectangle, if you use the shape of a rectangle, there must be an error. But you might say, okay, maybe I can choose carefully the height that the axis and the short will cancel out to 0. But how do you choose that height? If you don't know the actual area, we don't know what the height must that be. And we don't know the actual area. So there has to be an error, whatever you do. The only way you can decrease the error is what? Yeah. Yeah, you just can decrease the width of this rectangle. So how do you decrease the width? The width is dependent on the number of subinterval, right? You decrease the width by increasing the number of subinterval. So if you take the limit of the number of subinterval, then, so this is about limit now. So this limit might go something, so might go some number a, and we define this a to be the area of the region under the graph. The a is defined to be the area. That's the idea of integration. Whenever you say, might heard about the integration, something like, oh, integration is an opposite of derivative, or it's about just plug in numbers into indefinite integral, 부정적분 in Korean, or it's just the area under the curve. But if you think carefully, where do you get the concept of area? It's actually coming from the integration. So you have to start from the integration. But when you start from the integration, the concept of integration, you cannot think about the indefinite integral first. You have to think about the definite region, definite interval that you take on your x-axis and then subdivided it, and then looking at the actual value. So here is our definition. So a function f is called integrable. Just like differentiability, we have integrability. If the limit when n goes to infinity of I from 1 to n I from 1 to n, f of xi times xi minus 1 converges. So we can have a little bit modification of this. So we can choose not xi, we can choose xi minus 1, which is same as choosing the left end height of this rectangle. Or we can choose any height in between the left and right. We can choose any height actually attained in this subinterval in between the lowest point and highest point. So in any ways, it has to be attained by choosing a number in this subinterval and then computing the value of the function. So this xi could be replaced by any value in between xi minus 1 and xi. But I want to just write it this way, so make it simple. So you can see that, so this whole thing is about, we know the function, and we have a subinterval. Let's see, what kind of, so, and then it's also assumed that this subinterval are separated by this sequence x0 to x1, xn, and we can make it simpler. So let's see, where xi, so integrable on the interval from a to b, where x0 is a, x1 is a plus n b minus a, and so on. So xi is the ith point, a plus I times n b minus a, and xn is the last one, b. And then you can see that on the left, fxi is just a number, because we have xi exactly in the formula of a, b, and n, right? AB is constant because we fixed our interval. Whenever we talk about the region, we need to know exactly what interval we're talking about. And xi minus 1 also the same thing. So this part, this factor is about constant. And so everything seems like constant. Only thing that we don't have any control is n. A and b are fixed. I is fixed as 1 to n. So this whole expression is about expression of n. So this n is the only variable in our formula. So we take n goes to infinity of this formula. And if that converges to number, so now when you take the limit of n goes to infinity, no variable is left. Everything is just the number. Then if it converges, we call it integrable. Well, let's see. Let's try to compute the area of that. So if f of x is x squared, and a is 0 and b is 1, and we just put n to be n, then xi is 0 plus I n 1 minus 0, so just I over n, right? So let's compute the limit. When n goes to infinity, our formula is for I from 1 to n of xi, which is I over n squared, so that's fxi. And then what is xi minus 1? It's just the length of each subinterval, which is 1 over n, right? 1 over n. So n is constant to this summation, so let's take it out. We have n goes to infinity, 1 over n cubed, and we have I squared for I from 1 to n. So we know the formula of the square sum. Let's use it. So it's 1 over n cubed, 6 n plus 1, 2n plus 3 or 1. Let's see. If it's 1, then 1, 2, 3. Yes, 1. Okay. Right? So now you believe that this expression about the summation is everything about n. There's no other variable. We take n to be infinity. So what do we have? We have the cubic polynomial on the denominator. We have 6n cubed. And in the numerator, we have the highest degree is 2n cubed. And I don't care about the rest, because when n goes to infinity, the highest power dominates the value. So we only look for the highest degree. So the highest degree, if you compare these two, the coefficients, it's 2 over 6. So we know that this is 1 over 3. It converges. And so therefore, since it converges, we can say that this function is integrable. So this function, this f(x) equals to x squared, is integrable on the interval from 0 to 1. And what do we call this number? This number is called the integral. And we write that as this. Let me write it here. So so if it's integrable, we say a to be integral f of x dx is the limit of n goes to infinity of I from 1 to n of xi times x. So I can even just put it xi here. Xi times b minus a over n. Okay. So I replaced xi minus 1 into the step here, step size, b minus a over n. So this is our definition. Okay. So this whole thing, this whole thing is just one notation. This whole thing is just one big notation for a value, some kind of value. Okay. And the right-hand side indicates how to compute that value. So, for example, does this make sense? What does that mean? So when I give this kind of question, people say, we don't know. I mean, we can't find it. Why can't you find it? Because some people say, we don't know its antiderivative, or we don't know the indefinite integral of sine x squared. Because they think that we need to know the antiderivative or indefinite integral to find the definite integral like this to find its value. But as I said, it's nothing about indefinite integral. So in Korean, indefinite integral is 부정적분. The Korean high school education teaches 부정적분 indefinite integral first and then definite integral. But that's not how the mathematicians have developed the idea about this integration. So this only says that it's what? About the function y equals to sine x squared on the interval of 0 and 1, and this value is the area under the graph from 0 to 1 of y equals to sine x squared if this kind of limit exists. Okay? So this only indicates that this is what? Limit of n goes to infinity of I from 1 to n sine, here it's A is 0, B is 1. So if I just plug in there, so it's just I over n, and then 1 over n, which is this, right? So it only tells you that if you take the sum, let's say take n to be 10,000, 100,000, you get some number, right? That's the number that is approximate this value. It's so simple. This always exists. There is something, right? It's not that it doesn't exist only because you cannot find the exact value. There is some value. We only need to take approximation. So, so I'm kind of assuming that we know about the integration, but I still want everyone to be in the same pace. So raise your hand if you don't understand. You have a question?
Yeah.
Yes.
Where did you get n plus 1 multiplied to 2n plus 1 divided to 6?
Oh, here, this one. I see. This is just the formula of this. Yeah. I skipped we can prove it, but you can Google or ChatGPT ask about the proof. So raise your hand if you are not comfortable about the integration at all. Like I can go for a little bit detail. So I'm assuming that you kind of have a knowledge about integration of single variable function. But if you kind of forgot what that is, then we can go a little bit of brief review about the integration. Just raise your hand to indicate your background. So everyone is comfortable about this? You sure? Because I'm going to just go fast from this point. All right, so let's review. Let me give a definition, one definition here. So here the definition is that, so whenever we write this way, so this is a function whose derivative is f of x. We call that an indefinite function, an indefinite integral, but I don't want to use that word indefinite integral because it's somehow misleading that it's coming from this definite integral, that if you omit this bounds of definite integral, you kind of get the indefinite integral. But that's not the case. Definite integral is a number. Indefinite integral is a function, and they come from different perspective. The definite integral is about area. Indefinite integral is about now derivative. Okay. So for example, let's say, what is this? Everyone knows that. Just tell me what that is. Because no one raised their hands, so I think everyone knows what this is. What is it, Sandra? Yeah, well, maybe plus something. Yes, yeah. So every time they tell you not to forget plus c. So what does this means? Well, this is just a function, right? So c, let's say it can be any number. Yes, it can be any number, but it's a constant. So this is a single function whose derivative is x right here. So we call this function inside our integral symbol as an integrand. So whenever you get integrand by taking derivative of this formula, then we can say this is equal to that. So it's perfectly okay to say x dx equals to 1 over x squared, or you can also say this is equals to 1 over the x squared plus 1, whatever. Okay? So the curriculum tells you to put plus c with a c here to indicate that c could be any number, but well, in my case, as long as you know what that means, that in our definition, there's no contradiction here. All right, so then what is the relationship between the definite integral and this thing, so this is called the antiderivative, sorry. So let me put a name here. So this is called antiderivative. Okay, just another notation of antiderivative. So antiderivative is the function whose derivative is the original function, the integrand here. So what is the relationship between this one and the definite integral. It says, it's a Newton's theorem, a fundamental theorem of calculus. It says if, so if you take the derivative of a function whose value is defined to be, so x is already used, so let me use x. Instead of x, let's use t, the t here. If you take the function whose value is about the definite integral that contains x on the upper bound, then its derivative is the integrand. That's the fundamental theorem of calculus. This is fundamental theorem of calculus. So there are many fundamental theorems in mathematics. So this is kind of the most important theorem of calculus. And I'm not going to prove this. I mean, it's not because it's hard, but because it's the theorem itself is not that important, but you have to understand the meaning of this. So what does that mean? So when you have a function and you want to calculate the area of under the function, so this one, a to x, let's say a is here and you have x, and there is a part of your graph in between this interval, so y equals to f of x. What you're looking at so this graph is extending to some point, but you want to see the small difference in between x and delta x plus x. So in between here, what's going on? You want to see the rate of change of this part, of this area. So let's say x is moving this direction, and area is increasing, of course. But you want to see the rate of increasing of the area, and that means that it's increasing at the rate of this height, because f of x is the height at that point. That makes sense, right? Because you see, what did we do in the computing the area? We kind of approximated the area by the rectangle. So at the rectangle, you take a height at one point of this graph, right? So the rate of increasing of the area is just area divided by the rate of moving of this point. So therefore, you just remain the height. The area divided by the width is just the height. It makes sense. So and then let's just review other theorems. Again, when you have two functions multiplied, so let me write the multiplication symbol, f prime x gx dx, then this is same as, let me change the line, f of x times g of x from a to b minus of integral a to b of f of x gx dx. So this is called the integration by parts. Is that comfortable? That makes any ring or kind of familiar to you? If it's not familiar, well, let me give an example. So let's see. Oh, by the way, so you can, this is about the definite integral, but you can also do the same thing with the indefinite integral, because, let's see. So the fundamental theorem of calculus can also be written as the following. So if you have a function whose value is given by definite integral, then this is the antiderivative of f of x, right, by definition. So you can say that this a to b f of t dt is fb minus fa. So it can be any a here, not the same a, but if you have an antiderivative, you can always find it this way. So look at this integration by parts. You can separate out, so every part has its definite integral, and you can write it out into the subtraction between the values of this antiderivative. So integration by parts can also be written as if you take the antiderivative of f prime g, it's same as fg minus fg prime. Okay. This actually comes from the derivative rule. So let's look at the example. So let's say we have log x. I want to find the antiderivative of log x. How do we find that? Let's use integration by parts. So here, I'm going to think about this log x as a multiple of two functions. One is 1 and the other is log. So this is considered to be f prime, then this is considered to be g. And then on the right-hand side, so that's the left-hand side. On the right-hand side, I have fg. Now, I need to find f. If f prime is 1, f should be 1 or plus 1. I mean, f should be x, sorry, x. F should be x plus some constant, but I'll have to put any other constant than 0. So just x here. So x is our f. And then g is the original g, log x. And then take f, which is x, and g prime, which is 1 over x, right? So what do we have? X log x minus 1 dx. So here, our integrand is 1, which means that if I take the antiderivative, it must be x. So it is x log x minus x. Okay. Again, well, some people might not comfortable of not putting plus c at the end. And also, I didn't put the plus c here, right? I mean, not here, right? Doesn't really matter. If you put the plus c, what does it say? It means that if I have plus c here, then if I take the derivative, then I get this, which means that this is just the antiderivative. If I don't know what specific value of my function should be, then this is just one of the antiderivative that gives the derivative, same derivative here. So I can just say this. And I know that you guys had took course on engineering mathematics, and so there must be some time that you learned about taking an integral of cosine x exponential x, right? So how do you do this? By integration by parts. So here you take f prime and this as g, right? And what is it? Ex. So f prime. If f prime is ex exponential x, then f is just exponential x again, and then g is cosine x, and then you subtract ex times g prime, which is minus sine, right? And then you do the integration part again, right? By taking this one again to be f prime and this to be g, right? So then we have ex cosine x minus ex minus sine x minus ex derivative of g, which is minus cosine x, right? So what do we have? We have two of these, ex cosine x plus sine x. And here we have three minuses, so it's minus ex cosine x dx. So we didn't get rid of this integral sign, but you can see that the same thing happens on the right and the left. So you can combine these two to get 2 times of these is same as this. So therefore, it's same as 1 over 2 ex cosine x plus sine x. So this is also by integration by parts. Just reviewing, but if you have any question, let me know. So what are the, let me reuse this part. What are the other important theorem? We can have integration by substitution. The theorem says if you have fg times g prime dx, then this is fg. Okay. Integration by substitution. So how do we know that? Well, you can just substitute this to be t. So this whole thing is dt. So it's the same thing as ft dt, right? So let's use. So there is one condition when you use this integration by substitution, that this gx is 1 to 1 in a given domain. So if it's not one-to-one, you have to be careful when you do this. So whenever you take the antiderivative, it's just for computing the definite integral. So it's same thing when you put AB here. So it's going to be just AB here again when you want to find the definite integral. All right, so let's look at the example. Let's say you have this integral, definite integral. We don't know what exactly the antiderivative of this. We don't really know. I mean, you can find the approximate value by definition, right? And whenever you have a definite integral, you can always find the approximate value. But we want the exact value using this integration by substitution. Oh, by the way, so this is kind of a bit more application of a substitution. So let's see which one is better. I think I have a better one. So let me skip this for now and let's look at this one. So 0, 1. This one is better for now. So let's look at this first. So I want to find the definite integral of this. First, I want to, if I know the antiderivative of x times exponential x squared, then I can just subtract the values of that function at 0 and 1 to get the value of this definite integral. So what is the antiderivative of this? The integration by substitution says, okay, I can substitute something inside as g, and whatever outside should be g prime. So let's put this x squared to be g. And then we have x times dx. So this x must be g prime. But that's not the right g prime. That's not x, because g is x squared. Then g prime is 2x squared. So x must be 1 over 2 g prime, right? So if I write this way, this is 1 over 2 exponential of gx times g prime x dx. And then I can use the integration by substitution, which gives me 1 over 2 f times g, which is just x squared, right? So this is 1 over exponential x squared. So you can check whether this is correct by just taking derivative of this function. You take a integration, and this is a composite function, just take the chain rule, you get exponential x squared times 2x, cancel with 1 over 2, you get the integrand. Then how about this? So it's not exactly this theorem, but you can also use the substitution. So let's suppose we have x equals to sine t. So in this integral, I am changing x from 0 to 1. So if x is sine t, and this t and x has to be 1-to-1 correspondence, then t must lie between 0 and pi over 2. Because sine function looks like this. So it goes for here. So when it's pi over 2, it becomes 1. And it's 0, it's 0. Right? So t must range between 0 and pi over 2 to get x from 0 to 1. So in that case, then I also want to change dx to dt. Let's see. So t is from 0 to pi over 2. And if I substitute x by sine t, then the square root of 1 minus x sine square is cosine square. So cosine square t. And what about dt? So we have dx dt to be cosine t, right? So we kind of know that when you change x by dx amount, it will change approximately by cosine t times dt amount, right? So it's going to be cosine t dt, right? So let's finish our computation. So what is the square root of cosine square? When you take the square root, you have to be sure that whether it's going to be positive or negative, right? But when t is from 0 to pi over 2, cosine is also positive. So we can confidently say just this is positive because cosine is positive. So we have 0 pi over 2 cosine t coming from the square root here, and square, because another cosine is here, dt. How do you compute this? Cosine rule, what is it? 1. Anyone knows this? What is it? Cosine rule. Cosine square equals. You remember this? Okay. So if you don't know this, you probably couldn't enter here because you took the exam, right? The exam is on this week, on Thursday. So anyway, we can take the integral here now from 1 over t from 0 pi over 2. And then the integral of this is sine 2t from 0 to pi. But this part is okay because it's simple. Let's plug in pi over 2 here. It's sine pi, which is 0. And plug in 0, you get 0. So 0 minus 0. And here it's just pi over 2, so it's pi over 4. Okay, so we compute the integral, pi over 4, exact value. How do we know this is correct? Let's look at the meaning of this. So we have a function, y equals to 1 minus x squared. Y equals to 1 minus x squared, which means that it's y squared plus x squared equals to 1. That's the circle, right? So we are looking at the circular curve on 0 to 1. So we have a circle here, but we're only looking at this 0 to 1, this part. Is it upper part or lower part? It's upper part because it's positive. Y is positive, so we're looking at this part. And what does this definite integral say? This means that it's the area under the curve of circular curve. So this area is the definite integral. We know by the definition, the area of a circle is pi, and this radius is 1. It's pi, and it's a quarter of pi over 4. So we really didn't need to compute this way if you know the meaning of this. But we can have a different, several other ways to check the answer. So these are things that we can review from our past experience. Any questions about this? Just a review, right? Comfortable. It has to be comfortable. Let's change our perspective. Now go back. So this is just review. Let's go back to our definition of concept of integral. So if integral is about having an area, wouldn't be there another way of finding area instead of taking a thin rectangular region to approximate the region? So for example, if I have, let's say, if I have this region that we talked about before, so y equals to x squared, we kind of like had a thin rectangular box here to take the approximate value of the area. Can we take this region, like box from 0 to 1 here? And then how about this way? Just take a horizontal and vertical lines, and then we have a lots of rectangles, small rectangles, and count the rectangle that is inside of the region and multiply the area of a small rectangle. How about that? So the area of the region D is approximately number of small rectangle times area of small rectangle, assuming that each rectangle has the same size, same area. Okay? How about that? Makes sense, right? So let's try this idea to define our area. So I'm going to introduce a concept of partition here. So first of all, we need a big rectangle that contains the entire region. So first, let's suppose that D is properly contained in this big rectangular region. And then partition the interval AB and CD. So partitioning A to B is partitioning the x-axis from A up to N, which is B. And partitioning CD is partitioning y-axis. The y0 is C and y1 is C plus D minus C over N yn equals to D. We actually did this for a long time. When you make a graph of two variable function, we actually did the NumPy mesh grid function, right? Mesh grid, what do they need? They need two inputs, which is equidistance array of the values of x and y from the end bound to the other bound. So the x-axis from A to B, y-axis is from C to D. We use the linspace function to subdivide equally on these intervals, and then we put that as inputs of the mesh grid function. So once we have this, we can define the partitioning of this two-dimensional region as xi minus 1, xi times yj minus 1, yj. Right? So if you have a picture like this, you have A to B and C and D. The whole region is here, but you want to see at on i's subinterval here, and here we have j's subinterval here. There is a region that corresponds to that, right? So we call it Dij. And what do? Check or identify or check if Dij is actually lies inside of D. So if it contained in the D, so D maybe D is somehow this region, not the entire rectangle. It's kind of contained in the rectangle, but not entire rectangle. But you want to check whether your D, somewhere here, is contained in here. The problem is, what if it's partially contained? Shall we count that as it contained or not? No? It's up to you, actually. It's up to you whether check whether this entire small rectangle is properly contained or partially contained. Or you can check that like this. So if the midpoint, the center of the rectangle, is contained in the D, then we count it as contained. If it's not, it's not. It doesn't matter. Why? Because when you do this, your criterion is up to you. Criterion is up to your choice. So once you do that, you take the sum of all the small rectangle and then count the number of small rectangle that is contained in D according to your criterion, and multiply the area of the small rectangle, which are the same, which is B minus A over N times D minus C over N. And this is going to be approximate of the area of D. That's one way you can actually compute the area, right? So let's do it this way. How about this? As we did in the previous definition, I'm going to take the top right corner of the small rectangle Dij and conclude that Dij is contained in D if the top right corner point is in the D. So x, so it's not really x, it's the psi. So I'm gonna put psi ij to be 1 or 0. 1 if xi yj is lying in D, 0 otherwise. Okay, let's do this way. So I just chose my criterion. You can choose your criterion. Then let's try to do the step 4 and write the formula more concretely. We are looking at all the possible x subdivisions and all the possible y subdivisions. So therefore, there are going to be n squared number of small rectangles. And for each rectangle, ij, I'm going to check my criterion, whether or not I should include that or not. So it's either 1 or 0. If it's 1, then I'm going to add the area of my small rectangle. Right? That's the approximate area, right? So how do we get the exact area? So, for example, in this case, if I use this, then there's some box that partially contained, but not because the top right corner is not in the domain D, it's excluded in the count of this area, right? So there must be error. So we can take the limit goes to infinity to make actual area. So this will be the area of D. Make sense? So let me give a definition here. So this is now the concept of double integral. So in the double integral, what we are looking at in this case is that we have, in some sense, x-axis and y-axis and z-axis here, and we kind of put the rectangular box AB times CD here, and then here is our domain D. And then above this rectangular area ABCD here, there is a function called xi, xy. So this xi only takes the value of index, but I can also extend this definition to be, it's about function of xy, and this is about the inclusion of xy in D. And I can just plug in xi, yj here, right, to make the same computation, right? So then what is the graph of xi, xy here? So it's defined the entire region, but it's 1 or 0. The value is either 1 or 0. So it's 0 here, but it's 1 on top of here. It's 1 here. So I'm kind of finding what? The area on the down on the xy plane times the height of this graph. So I'm kind of finding the area by finding the volume of this region under the graph of xi. So here. So this volume is same as the area of D, right? Because height is 1, so you just count that as a, just don't think about the unit here, just number. As a number, the volume is same as the area. So let me define the notation here. So a two-variable function, xy, is called integrable. Again, I'm just extending the definition of integrability of the single variable function. If I take the double sum from I to 1 on A, B, C, D, and j from 1 to n, f of xi, y, j times here b minus a, d minus c exists or converge, then we call it integrable. Same definition. But you have to understand what's going on here. So we have here the area of subrectangle on xy plane. And what is this? This is the height. Area times height is volume. We are talking about the volume of under the graph of two-variable function f. So this is denoted as xy dx dy. So in other words, since we have the area ABCD here, AB times CD. So we have a double integral sign here, and below that sign we have the notation of region that we are interested, and we have an integrand which gives us height, and dx dy is just the addendum here. And this is the area, volume under the graph or surface of z equals to x comma y. Okay, so let's compute something here. So let's look at the examples. So whenever you see the double integral, think about the meaning and also the formula here. Think about meaning and the formula. So let's see, we have 0, 1, 0, 1, x, dx, dy. So we want to find this, and what is the meaning of this? There is a two-variable function whose formula is just x. We want to look at the volume under the graph of that two-variable function over 0, 1 times 0, 1. So let me draw the graph here, x, y, 0, 1, 0, 1 here. And what is the graph of y, f of x, y equals to x? It doesn't matter what y is, only depends on x. So it's going to be somewhat slanted. It's increasing by x increases. So it's going to be look like this. So this is the graph over 0, 1, 0, 1. And if you look at the volume or region under the graph, it looks like a prism here. Does that make sense? Look carefully about the graph here. I want to find the volume of this prism. Well, there are two ways. One is you use the limit like this, or you can have the obvious computation. So if you just rotate your prism on the 90 degree, let's say this is your bottom of your prism. What's the area? 1 over 2. And what's the height? 1. So the volume must be 1 over 2. Let's check if you get the 1 over 2 by taking the limit. So by the definition, as the limit goes to infinity of I from 1 to n, j from 1 to n, and the value of function. So it's just x. So x only depends on I, index I, so it's I over n because our starting point is 0 and end is 1 for x and y axis. And then here, these two, it's 1 over n squared, right? So what is the summation? So first of all, there are n cubed, take that out, and we have the integral of j, and there's no j inside. So therefore, it's always the same. So it's just n times I from 1 to n, I. So what is this? If you take the sum of 1 to n, it's 1 over 2 times n plus 1, right? So what is the limit? So in the upper part, you have n cubed, and on the denominator, you have 2 times n cubed. So it's 1 over 2. Okay? Am I going too fast, or is it okay? If you get the concept right, if you have a clear concept, that's fine, because we're going to talk more about how the technique of computing the double integral. But right now, I'm trying to give you the clear concept of double integral. Is everything okay? Okay, so even though there's no feedback, I think I kind of doubt that you got the clear concept. So I'm going to repeat, maybe summarize what I just said here. So really, this is not about integral. It's called double integral. Double integral. And this is a notation of double integral. This whole thing is notation. Double S, the integral symbol, is a notation. This notation of indicating the region also has to be down under this double integral symbol. And this is also in the symbol that goes inside the integral symbol that indicates what function are we looking at. And dx dy is, if you go deeper, then it has a meaning. But now, right now, it's just addendum here, just to say that this function is of x and y coordinates. And this is a number, okay? This is not a function. There's no definite or indefinite integral when it comes to the double integral. It's just the number, always the definite integral. And it is defined to be the limit of this. Sorry, x, not j. Let me write this way. yj. Let me write this also in the notation of a and b. So a plus I times b minus a over n, comma c plus I times d minus c over n times b minus a times d minus c over n. Just a quick remark, if anyone knows or heard about the double integral or integral at all, I use this specific value of the point only because I assume that the function is integrable. If it's integrable, I mean, the general definition of this limit is you have to be able to guarantee that the limit exists for any type of xi or ji as long as this xi, ji lies in the subinterval, sub-region. But here I assume the function is already integrable. So I can just fix one xi and ji to put in our function to get the height. And then I'll always get the same value because that is guaranteed by the integrability of the function. So, so if you want to see the more detail about what I just said, you can go to my book and then read part in chapter 7. So that's your double integral. And the meaning of is the volume under the curve, under the surface of the graph of the function f. So, any question about the concept here? Again, we are taking the volume of cubes, height times the area of a cube, thin cube. Okay, so let's now talk about how to really compute something with this. We know the definition, but knowing definition, I mean, definition always gives some answer. I mean, hypothetically, I mean, I theoretically give the answer, but in real life, you really want the answer maybe in an accurate number. So how do we do that? So there are many techniques of doing that. So here's one technique. It's not example, so it's a theorem. It's called Fubini theorem. So think about our domain is the rectangular domain. Okay. So then, when you take the integral of this two-variable function, you can pretend that this double integral consists of consecutive integral of single variable functions. So first of all, a, b, and c, d, and f of x, y, dy, and dx. So I'm introducing different concepts. This is not double integral. This is the double integral. This is called iterated integral. Okay? In Korean, 반복적분. So it's not that we are taking two-dimensional region. We are taking, each time we take the integral, we take one-dimensional interval, and then we do it consecutively. So I'll give you the picture in 3 dimensions. Let's say we take the same picture I did draw before. So we have this picture. So this is x, and this is y, z here. So my a, b, c, d are 0 and 1. So in this case, let's see, our 0, 1, 0, 1 of x dx dy. If I just apply to Fubini theorem, becomes 0, 1, 0, 1 x dy dx. So first, I'm taking a derivative of x in terms of y from 0 to 1, pretending that x is nothing to do with y. So it's something like similar to, idea is kind of similar to partial derivative. We consider x is constant, relatively constant to the variable y, and pretend that we're just taking a derivative of a function of y. So let's say we have x here. We're looking at here. So our section is, our section is here. We're taking kind of a section. And I'm making a y change from 0 to 1. So my y is changing along this line when x is x here, right? And then what I'm doing is I'm taking a height of x, which is value of function. This is the height of x. And then integrate over 0 to 1. So what I get is the area of this section. So this is integral from 0 to 1 of x dx, x dy, right? So this is going to be a value depend on y and depend on x, right? So when I take an integration, I'm pretending x is constant or fixed, but x is also could moving. It's only when I take integration that I assume that x is fixed, but after I take the integration to get the area of this section, now I can move my x from 0 to 1. So that's what is happening in the next integration. So this thing becomes 0 to 1 of this ax, and integrating over x from 0 to 1. So I'm taking this section as an area, and then I'm moving this section by moving x-axis from x point from 0 to 1, and then I'm integrating. So what I'm integrating here is same as the meaning of integration. So in this case, we cannot just say ax is the height because we are taking a volume here. So consider dx as somehow the small increment of x. So you're x changing in a dx steps. So when x is changed by dx, you get a different place, and your section will be changed. But approximately the volume between these two sections is approximated by the cube. And this cube has area ax, and since it's moved by dx amount, the height is dx. So if you multiply these two, it's the volume of a small cube, a thin cube, in between two layers of sections. And then you're integrating all together from 0 to 1. So you're kind of stacking all the thin layer of sections, thin volumes together to get the entire volume. So therefore, the meaning of this is just same as the meaning of the double integral, giving you the volume of the entire region. You can actually do the opposite way. So here I did the integration y first and then x, but you can change the order. You can do the integration by x and then y. So what does that mean? So we can take this dfxy dx dy, and then instead of ab, we can cd and then ab xy dx dy. That's also possible. So in this case, let's draw again. So what does that mean? If I change the order of this iterated integral, I have the same region, or three-dimensional region, but this time I'm fixing y first. So here I'm taking 0, 1, 0, 1, 1, x dx dy. So here, if I look at the inside integral here, I'm changing x, considering y is a kind of constant. So here is y-axis. Let's say my y is right here. Then my section is this, right? Triangle. And I'm looking at the area of this section by taking an integral here. So let's call this bx. By. What is it? So I'm changing x from 0 to 1. So this is x-axis. I'm changing x from here to here. And I'm looking at the height of x, which is height of this section. I'm integrating it. That means I'm looking at the area under this line. on this plane. So I get entire area of this section, which is triangle. And I can actually do this pretending that this is the single variable integration. So by is just integrating x from 0 to 1, which is 1 over 2. So you can see that the section is always the same area, no matter where I took a section. So y changing, but the section, the shape is not changing at all. So it's always 1 over 2. And then what I do next is integrating this by over dy. So I'm changing my y here, right? And then my section also supposedly change in the ideal case, but this case there's no change because by is always constant, 1 over 2. And this, whatever that is the area of a section, and this is the height of the volume in between these two sections, and you multiply them to get the volume of the cube, which is thin cube here. And you add all these thin cubes, you get the entire volume, approximate volume. But when you take the integral, we're kind of approximate, and we're kind of taking a limit of the approximation by making infinitely many subdivisions to get the exact volume. So therefore, you get the entire volume under the graph. But the difference between here and here is the direction where you cut the section. The idea is the same. You want to get the volume. And the volume is the double integral. The Fubini theorem says that you can get the volume by cutting the volume into two different ways, and they have to be always the same. So there is a big one important condition in Fubini theorem that this function is this Fubini theorem the condition is that this function has a continuous partial derivative. So it's not enough that this function is integrable to get the Fubini theorem. Your function has to be continuous when you take the partial derivative. So there are two partial derivatives, right? F of x and f of y. If those two functions, as a two-variable functions, are continuous in the given domain, then the Fubini theorem holds. If it's not, then there is a counterexample that you get the different answer. So I don't want to go over these counterexamples and detail about the condition, but because most of the times then you're dealing with the function very nice, which has continuous partial derivatives, and I think it's important to get the idea first correct, then go for the tedious mathematical part. I'll give you another example. Let me see if you can follow this through. So let's see. We have 0, 1, 0, 2, x plus y, dy dx. So how do you compute this? Well, just the same simple question, but I just want everyone to be comfortable about looking at this. So whenever you have this, even though sometimes people omit this bracket here, you kind of understand the order of dx dy gives you the order of the integration. So in the double integration, dx dy always comes in this pair. This is just one notation here. But in the iterated integral notation, the order of dx and dy is important. So this is not the same as writing dx dy in this order, because it changed the domain first. This means that x is from 0 to 2, y is from 0 to 1. But if you say this way, y is from 0 to 2, and x is from 0 to 1. Okay, so order, you have to think about order. And you have to keep the order of taking integration. So first, what is it? You take the integration of x plus y, pretending that x is constant to y, and just take the normal integration of y. Then x is a constant. What is the antiderivative of x? Yes, xy. And then what is the integrate derivative of y? We know that's y squared, right? And then we're taking 0 to 2. Okay. So in this case, it's for y. We're not changing x. Okay. So what is this? The inside, it's 2y plus 2, right? And then it's 2y, not 2x, sorry. So 2x plus 2. And then you take the derivative of x. What is it? So x squared plus 2x from 0 to 1. So it's 3. Okay, so if I wrote this way, what do I trying to compute? I'm trying to compute the double integral of what? Of function x plus y. So in double derivative notation, dx dy always comes in this order. And what's the domain? The domain is x from 0 to 1, y from 0 to 2. Okay? So I'm computing this double derivative using the Fubini theorem, and it's 3. Make sense? Okay. All right. So here, what I just defined so far is about double derivative on the rectangular domain. How do we define the derivative on a non-rectangular domain? So if you have non-rectangular domain D, and you still want to define what this is, so the meaning of this is you only want to look at the graph of function which is lying on the D. Not the entire domain. I mean, there's no rectangular at all. The D is just the random region in xy plane. And you just want to take the portion of your graph lying above this D. But still, you need to know how to define it. The way you define it is by taking a big rectangle, AB, CD, that contains D. And then you're taking integration. Sorry, so let me erase this part too. You're taking integration of this function f times psi of dx dy. So what is f times psi? It's not composition, it's a multiplication. So when you take point xy, this f times psi is just simply take the value of f of xy and psi of xy. And psi is the same psi I just mentioned, 0 or 1, depending on whether xy lies on D or not. So if xy lies in D, psi is 1. So you get the normal value, f of xy. If it's not, then psi is 0. No matter what the value of function is, it's always 0. So this function is still very nice function because it's always defined, but to some value, it only differs by the inclusion of this point into the D. But xy can vary in between this rectangular region, and I'm just changing the integrand is this, not the f, because original f is only defined on D, but here I'm changing it to have a function to domain which is bigger than D on the rectangular domain. So in some sense, let's see this way. So here is the three-dimensional picture, and here's, let's say this is our the original graph, but let's say D is somewhere here inside of your rectangular domain. When you write this way, I don't care about outside of D. I only want to know what's inside here. So I want to know the volume over the region D. So in order to find that, you kind of kill all the values outside D. So it's kind of leaving only this part, and all the other parts outside D has a value 0, like this. So in that way, you can properly compute your limit, because now your domain is rectangular. Before then, there's no way you can compute, right? There's no rectangular domain to partition your x and y axis. So that's a proper definition, and I'll give you another version of Fubini theorem. And then suppose that your domain D lies inside a big region, okay? And it's not rectangular, so let's say this is not rectangular domain. Then how do you compute D? So we assume that D is somehow bounded by graph of one variable function. Suppose that I have this big region, A, B, and C, D. D is somehow this region, D here. Okay, so we are missing some point here, right? Then to get the domain, to get the double integral only on this part, I don't want to compute this part, this white part. So I take the upper bound and lower bound. So let's call upper bound to be the graph of y equals to g2x, and the lower bound to be y equals to g1x. And then Fubini theorem says this, g1x, g2x. So the double derivative of the function over the domain D, which is originally defined in this way on the rectangular domain that contains D, can be computed by iterated integral, first by y from G1 to G2, and then from A to B for x. So this is your x-axis, and this is your y-axis. Imagine that there is a z-axis coming through the blackboard here. The function, the graph of function fxy is lying above this blackboard. You want to find the volume under this graph, which is lying above only on this domain D. So first, you fix your x, kind of x here, right? You kind of have a section here. But when you cut the x, when you cut the section at x, you're not cutting only the region, two-dimensional region. You're kind of cutting the entire three-dimensional region perpendicular to this blackboard. So you're going to have a area of a section, right? So how do you get the area of a section? First, you take the height. This f of xy is the height. And then you take the width of this section, the rectangular width of the section. And this width, take the width, your, x and y is changing. Yes, to take the width, your y is changing from here to here, not from entire C to D. You want to restrict your range of y only from the lower bound to the upper bound of your region D. That's your bounds here. This bound, the lower and upper bound, depend on the value of x. Right? So you do this for every x. First you do this for single x, assuming that x is fixed, and then you get the section, area of a section, and you do this for every x. So you get a stack of sections, and you want to find the volume between these two sections, which is the thin volume section of the region under the graph of f. Then you add them all to get the entire volume. So this is one of the Fubini theorem. So only when you have D given as the collection of all points where y is from g1x to g2x, and x is from A to B. Okay. So you can do the opposite way too. We're going to do it next time. So if you, it depends on which way is easier to cut your domain. So in this way, it's easier to put the lower bound and upper bound. But if the figure is 90-degree rotated, then it's easier to put the lower and upper bound for x instead of y. So in that case, you can switch to x and y to get another version of Fubini theorem.